All right, let's talk about the bell work. How would you go about doing the first question? Yes, ma'am. Yes, we're going to take this 2. We're going to do 3 times 2 because I'm going to take this, I'm going to put it in the place of the x. We're going to substitute it in there. And why would you multiply the 3 and the 2 first before you add the 7? PEMDAS, order of operations. So I would have 6 plus 7 equals y, which means y is how much? 13. How would you do the second part of the question then? Yes, ma'am.
25 minus 7.
You did what?
I did 25 minus 7.
25 minus 7. So we would use substitution here again, and I agree with your first step. So I would have 3x plus 7 equals 25, and then you said you subtracted 7 from both sides. Wait, on the last problem you guys told me to start with multiplication, and you said the reason was order of operations, right?
Yes.
And then we did the addition. So why aren't we starting the same way here? We're trying to find the x. Yeah. So looking at this here, let me write this down for just a second. This would give me 3x equals 18. So the first problem, this right here, all of my numbers are together on the left side, right? And my variable is all alone on the right side. We are simplifying here. Which means I follow order of operations, PEMDAS, from the top down. Like this. On this one, we go backwards because we don't have a variable all alone on one side. It's not numbers all on one side and the variable all by itself on the other side. We're trying to get the variable all by itself, and in that case, the process is called solving. And so it's just like when we were working on solving our quadratics. We want to go backwards through the order of operations. We're looking for x, for a solution. Anytime I'm going to do the operations that are in front of me, I'm simplifying and I follow order of operations from the top down. Anytime I want to get things to cancel so that I can get rid of them and I'm going to do the opposite of what I see, that's when I go backwards through the order of operations. We're going to be talking a lot about these processes here in this next unit, all right? It's going to be really important to know whether we are solving, trying to get something alone, or simplifying, just doing the operations that are in front of me. Go ahead and flip in your books to page 111 for me. Page 111. We're going to talk about some familiar terms and some not so familiar terms. Domain and range have come up for us. When we were talking about parabolas, we talked about the domain and the range for our different parabolas. Domain is all possible x values. All possible x values. This is my independent variable. We can also talk about it as the input. Domain and range have a unique relationship. Let's see if we can use what we wrote down for domain to talk about what the range is. If the domain is all possible x's,
All possible y.
the range is all possible y's. Dependent variable, yes. That's absolutely correct. Domain is my input, range is the output. So far, so good? All right. I want to talk for just a moment before we talk about functions, independent and dependent variable. Your dependent variable, you can't find a value for that until you know what the input is. Kind of like if you're trying to estimate your check at work, you would first need to know how many what?
Hours you work.
How many hours you worked. And then you could make a reasonable estimation or a reasonable guess about what your paycheck would be. I know sometimes the taxes get a little bit screwy. I'm going to go back to this idea of working a job for a certain amount each hour a lot of times when we're talking about functions because it's one of those relatable concepts. In order for something to be a function, each input, x value, has only one output, y value.
Oh, yeah, you don't learn like this.
Mm-hmm. Each input has only one output. Yes, ma'am.
Did we learn that like if they had like the same output or something, it was something they all connected or they all had the same. It was something that the numbers repeated in the output.
Mm-hmm.
I forget what it was though. The learning did.
Yep, we'll actually talk about that here in just a second. In order for something to be a function, I'm going to go back to that idea of a job, okay? If you worked 5 hours this week and you got your paycheck on Friday, and you worked 5 hours next week, your paycheck that Friday should be
Same.
the same. If you worked a different number of hours, your paycheck should be different. In order for it to be a function, that means that if you know the input, you can accurately predict the output. If you get paid a salary, does anybody know how salaries are different from hourly jobs?
Yearly or monthly?
Yearly, monthly, does the paycheck change?
Yes.
If you're on salary, paycheck stays the same, week to week, month to month. If you don't get a raise, then year to year. If you're on a salary, everything stays the same.
Like every 2 weeks or something.
Mm-hmm. Those would also be functions because you could accurately predict the output. That's what makes something a function. If you can accurately predict the output when you know the input, it's a function. We have a way of testing for functions on graphs using something called the vertical line test, and I'll show you how to use that in just a moment. So on a graph, we can use the vertical line test. Function notation. Does anybody know what I mean by function notation? Yes, ma'am. Yep. We're going to have the function's name first, like function f, and then inside parentheses we have an x. because that is our independent variable. In story problems,
Does it mean that never changes?
the independent variable will always be inside parentheses, yes. In story problems, you saw when we were talking about parabolas, sometimes I use different variable names because it makes sense in my story. Then I'd have a different independent variable, but that's what would be inside the parentheses. Does it always have to be an F at the beginning? No. You might have h of x, or you could have g of x, or t of x. The letter at the beginning doesn't matter. That's the name of the function. But this notation where I have a letter and then parentheses with my independent variable name in between, that's my function notation. And when we look at our function notation, this idea right here, the whole thing, means the same thing as y. So this whole thing together means the output. Which means if I'm looking at an equation and it has function notation, if I want to replace my function notation with the letter y, I can do that. It has the exact same meaning. You guys okay with that so far? All right. Let's look at a couple examples here, and we're going to determine whether or not they are functions. You guys ready? Okay. Mm-hmm.
The x's can repeat, but the y's can't. It goes the other way around.
Mm-hmm. I want to know whether each relation, that's just when I have sets of numbers that go together, is it a function or not? What do you guys think about this first table? Not a function. Why?
Because the x repeat.
The x repeats. What about the y? Y is different. So this is why I go back to thinking about a job here. The input would be like the hours that you worked, and the output would be like the check. You work 5 hours, you get $1. First of all, that probably means you need to find a different job, right? But we're just pretending for a minute. You work for 5 hours, you get $1. The next week you work for the same 5 hours, but now your pay is what? $2. Does knowing the number of hours you've worked help you accurately predict your paycheck?
Yes.
In this situation?
No.
Not in this situation. That means it's not a function. If the input doesn't allow you to accurately predict the output, it's not a function. The input of 5 has 2 different outputs. If you know the input, you should be able to accurately predict every time what the output is. If you can't, it's not a function. What about this middle table?
Yeah.
That one is a function. Every input has its own unique output. Well, let's look at it. The third one. The third one is kind of like if instead of getting paid by the hour, you get paid for doing a job, like raking your neighbor's leaves. If your neighbor says, I'll pay you $35 to rake my front yard. If it takes you 1 hour, how much do you get paid?
35.
If it takes you 7 hours, how much do you get paid?
35.
So no matter.
Are you able to accurately predict the output?
Yes.
Then it's a function. The y's can repeat, the x's can't. Because remember, we want to be able to accurately predict the output. If I can accurately predict the output, even if the output doesn't change, I can accurately predict it. It's still a function. So this one is yes. Each input goes to only one output. I could draw a slightly different representation to understand this better. In this first table, with an input of 5, it's going to 2 different things, so I can't make predictions from that. But in this third table, I have different input values that are all going to the same output. That's okay. Remember, the goal is accurate predictions about what's getting ready to happen. You guys okay with this so far? All right, let's look at how to use that vertical line test. So down at the bottom of page 111, the vertical line test is a visual way for me to check to see if each input has one output. If I hold up a vertical line, like my pencil, and I run it across the graph like this, anywhere that graph touches my pencil, that would be a point on the graph, right? And I could write an ordered pair for it, an x, y. Right here, the x value would be like, I don't know, -5. Over here, my x value would be a positive, right? So each ordered pair would have a different x value, a different input. What I'm looking for, let me trace over this thing. If I draw a vertical line right here, how many times does that blue graph cross my vertical line? Just once, right here. What about if I did a vertical line over here? How many times does the blue graph cross it? Just once, right here. That's what it looks like to be a function. No matter where I put my vertical line, it only ever crosses it once. When it fails the vertical line test, let's come over here and look at this like parabola on its side. Do you guys see how if I draw a vertical line right here, it crosses twice? On this right here, the x parts of those ordered pairs would be the same, but the y's would be different because they're at different heights. So this would be like, I'm going to make up some numbers here. This would be like 3, 2, and down here would be like 3 and -2. Same input, different outputs. I want to look at these 3 graphs to see if they are functions. So we've got this squiggly right here. Is there anywhere, if I hold my pencil straight up and down, is there anywhere I could put my pencil where that red squiggly crosses more than once at the same time? No, that's a function. As my reason for that, I could say that it passes the vertical line test, because that's another way of checking our inputs and outputs. A lot of times we'll use VLT to mean vertical line test, because it's a lot shorter to write. All right, let's look at that middle graph now. Oh goodness, sorry, my thing just screwed up and made that really hard to see. There we go. I'm going to go over this one in green. So here's the graph that I'm looking at. I'm going to take my pencil. If I put it right here, does it touch the graph at all?
No.
No. That's okay. That doesn't mean it's not a function. If I run my pencil across here, I finally get to the graph when I'm right here, right? It crosses it more than twice, right? Every single point on this line has the same x, but a lot of different y's. So I could write down some of these ordered pairs. This would be like 2, 3 up here. This is 2, 1. This is 2, -2. Lots of different outputs, not a function. This fails the vertical line test. What about this upside down V shape over here? Does it pass or fail? Lauren says it passes. What do you guys think? Yes, this one is a function. Passes the vertical line test. You guys all right with that? All right, turn to page 112 then. Now that we've talked about what it is to be a function and whether or not something is or is not a function, we're going to grow our understanding of this, and we're going to talk about a special type of function. It's called a one-to-one function. Kind of like if I was going to talk about an animal that you've never heard of. We'll pretend for just a minute that that's dogs. I know everybody in here has heard of dogs. But before I could decide if something is a golden retriever, I would first need to know that it is a dog. If it's not a dog, can it be a golden retriever? No. So one-to-one functions are very special types of functions. In order to be a one-to-one function, first, we have to know that every x, every input, has only one y, one output. And there's one more criteria, because this much right here just makes it a function. Every output or y value comes from only one x value. Every input, every x, goes to only one y. That makes it a function. Once we know it's a function, we can check to see if it's this special type of function.
So if the first one was like 5 and the second one was 1, then the one can only be to that 5 again. Is that the other?
An inverse function. An inverse function undoes what the original function did. You guys are actually already familiar with this idea of an inverse. We've just never talked about inverse functions before. If I want to undo addition, what do I use? Subtraction. Addition undoes subtraction, subtraction undoes addition. Those are inverse operations. What undoes multiplication? Division. Those are inverse operations. Instead of just looking at a single operation, an inverse function is an equation that undoes what another equation did. Inverse function notation. This one looks a lot like our regular function notation. Like I'm still going to have the f, I'm still going to have the x inside parentheses. It has a little -1 that looks like an exponent on the function name. So you might see that with g of x. You might see that with h of x. When you see that little -1 right there, it doesn't actually make anything negative usually, but it does tell me that this one undoes what the other one with the same name is doing. If I don't see that little -1, it's not an inverse function, or at least I don't know that it's an inverse function. If I see two functions, g of x and g with the little -1 of x, then I know that they undo each other, just like addition and subtraction would undo each other. Make sense? No? We'll use it a lot more in the future, and you guys will get to see that one undoes what the other one did. I want to look now at a couple different representations, and we're going to try to determine whether these are one-to-one or not. So I'm looking at the same set of 3 tables that we looked at previously. This first one, did we decide that that one was or was not a function?
No.
Very first table?
No, it wasn't.
Why not? Yeah. 5 went to 2 different output values. This one was not a function.
It's not a one-to-one function.
Correct. It can't be a one-to-one function if it's not a function to begin with, just like it can't be a golden retriever if it's a fish. If it's not a function, it can't be a special type of function. The one in the middle, was that one a function?
Yes.
Yes.
And it's a one-to-one function.
How do you know?
Because the outputs only go to the, like, 1 only goes to 4 doesn't go to 2 or 3 or 4.
Mm-hmm. This is one-to-one. Every output came from only one input. So I'm going to go back and talk about a job again. We talked about jobs and functions. If you get paid $5 an hour and you work for 5 hours, how much will your check be for? Assuming, like, let's not take out taxes or anything. If you get $5 an hour and you work for 5 hours, how much is your check? $25. If you get paid $5 an hour and you work for 11 hours, how much is your check? $55. If you know the number of hours, you are able to accurately predict the check amount, right? In a one-to-one function, it also works the other way. If you know how much the check is for, you can accurately predict how many hours were worked. So let's pretend that same situation. You come home from work and you tell your parents, you're like, yes, I got a $45 check. And your parent says, I know you worked for how many hours if you're getting paid $5 an hour? 9 hours. You can accurately predict the input if you know the output, if it's a one-to-one function. Yes, ma'am?
I have a question. You know how when you work, you have training before
I can talk about that in just a minute, but I will address that idea because that's a really good one. Third table here. Was that one a function?
Yes.
Can you accurately predict the output? Yeah. The output every time is how much? 5. So you can accurately predict it. It doesn't seem to matter what the x's are. The output is always the same. This is a function.
That's an inverse function.
Is it one-to-one?
No.
Does knowing the output allow you to accurately predict the input? No. If I tell you the output is 5, I made $5 today.
And then you said the next. It could be 1, 2, 3.
Yeah, you're like, I don't know whether you worked 1 hour, 2 hours, or 3 hours. Because all of those had the same amount of pay. Yeah, not one-to-one. My reason for that, I would say the output of 5 came from more than one input. So one more time. To be a function, that means if I know the input, I can accurately predict the output. That has to be true for it to be a function, and it can't be a special kind of function unless that's true. To check to see if it's a one-to-one function, that means if I know the output, I can accurately predict what the input was. If I can't make an accurate spot-on prediction about the input every single time, then it's not a one-to-one function. All right, let's look at some graphs and then I'll talk about that question. So I'm going to flip the page now. So we're going to be on page 112 and then a little bit on page 113. So I'm down at the bottom of page 112, but the graphs we're looking at are on page 113. To check to see if something is a function, I use what kind of test? Vertical line test. Once I know it's a function, I can use the horizontal line test to check to see if it's one-to-one. So this first graph right here, that's squiggly. We talked about that one already. Was that one a function or not?
Function.
This one is a function. Because it passes the vertical line test. Then I go to check it with a horizontal line. If I hold my pencil this way, is there anywhere I could put my pencil on here where it would cross my pencil more than once?
Yeah.
Yes. Fails the horizontal line test, so it's not one-to-one. Like if I put my pencil right here, it crosses in 1, 2, 3 spots. So not one-to-one. Fails the horizontal line test. This line here in the middle graph, not a function. Correct. Can't be a special kind of function if it's not a function to begin with. Absolutely correct. All right, now I've got this V shape. Was that V shape a function? Yes. Why not? Yep. Passes the vertical line test, so it's a function, but it fails the horizontal line test. So it is not one-to-one. Like if I put my horizontal line, say like right here, it would cross in 2 spots. Remember, it's if you can do it anywhere on the graph. Yes, ma'am. Yep. On that particular graph, it would do that anywhere except right at the vertex. What about this line down here? Is that a function?
Yes.
Yes. Is it 1-to-1?
Yes.
Yes. This is a 1-to-1 function. It passes both tests. Vertical line test and the horizontal line test. What about this parabola here? Is that a function?
No.
Vertical line, does it pass?
No.
Yeah.
Yeah. Horizontal line, it doesn't pass. So yes, it's a function, but it's not 1-to-1. What about that last graph? Does it pass my vertical line test? Yep. Does it pass a horizontal line test?
Yes.
Yes. So this one is also 1-to-1. So I would have the same thing on that one. All right. Your first homework assignment for this unit is not due until Wednesday of this week because we're going to keep talking about functions in 1-to-1 tomorrow. Your test over Unit 3 is also the midterm, and that will be Thursday the 30th. That's a week from this Thursday. This is a very short unit. All right? Have a fantastic rest of your day, guys, and I will see you tomorrow.